Okay, this is the second video for IB Quantum Mechanics. Our first video we explained the photoelectric effect. You shine light on a metal, it ejects electrons. And one of the very strange things that happened was that the stopping potential, at a certain potential, no current flowed, which told us that there was a certain maximum energy that any electron could have. And we also found that that maximum energy depended on the frequency of the light. So high frequency light can give an electron more energy than low frequency light can. And remember, the graph looked like this. The energy that was given by the electron, or by the light, turned out to be linear with the frequency. And the key thing that we come up with is the idea that the maximum kinetic energy equals HF minus phi. In this equation, Kmax is the maximum energy the electron can get. Phi is the work function of the metal, the minimum energy required to break it loose. And HF is the energy carried by the light, where h is Planck's constant. That was the slope of the graph in the previous slide. Has a value of 6.626 times 10 to the minus 34 joule seconds. And f is the frequency of the light. And what we come up with this is that light can only carry energy in discrete amounts, and we call that amount a photon. And the energy carried by a photon can be given to exactly one electron. Also, each electron can only be hit by one photon. And that explains why there's a maximum kinetic energy, because each photon carries HF energy. Since each electron can only get one photon, that means that no electron can get more energy than h times f. And this is important. The energy of each photon is proportional to its frequency, E equals hf. This is the interpretation of the photoelectric effect that got Einstein his Nobel Prize. So let's look at an example here. Let's say we have light of wavelength 450 nanometers, that's blue. It's incident on a metal plate. The stopping voltage we find is 1.7 volts. We want to find the work function of this particular metal. So the first step to finding the work function is that we need to find, first off, Kmax. Kmax is equal to the charge on the electron times the stopping potential, which is 1.7 electron volts. In a lot of cases, quantum mechanics, it's going to be very useful to work in electron volts instead of joules for a unit of energy. 1 electron volt is equal to the charge on the electron times 1 volt, or 1.6 times 10 to the negative 19 joules. That's a conversion you should be able to do easily. And so we know the wavelength of the light, and that means we can find the frequency of the light, and from that its energy. So hc over lambda gives us the energy of the light, or of one photon, and if you plug the numbers in to your calculator, you find that it is 4.42 times 10 to the negative 19 joules, converting to electron volts, 2.76 eV. And now we only have one more step. Remember, the maximum kinetic energy equals the energy of the photon minus the work function. So the work function then equals the difference between Kmax and E, which is 2.76 electron volts minus 1.7 electron volts. And we find that the work function of this particular metal is 1.06 eV. And that is fairly typical of the examples that you'll see related to this. Now we want to find the longest wavelength of light that will produce photoelectrons. Now remember, as the wavelength increases, the energy of the photon decreases. And if the photon energy drops below 1.06 electron volts, then you won't get any photocurrent. So basically we're saying that 1.06 electron volts equals the photon energy hc over lambda. But first we need to convert that 1.06 electron volts back to joules. And that's 1.697 times 10 to the negative 19 joules equals hc over lambda. Solving for lambda, that becomes, let's see, we get a wavelength of 1.17 times 10 to the minus 6 meters, or 1,170 nanometers, which is well into the infrared range. And that is a fairly typical example. And that brings us to the end of our second video, where we explore the theory of quantum mechanics that was based on those photoelectric effect experiments. It turns out this was not the only piece of evidence for quantum mechanics. The other one had to do with blackbody radiation. Max Planck solved that particular problem there using the same notion that light carries energy in discrete amounts. And the amount of energy carried by one photon in his theory was also h times f. And that was why people decided that quantum mechanics, while it might be weird, is a very, very useful scientific theory.